this talk, but we'll continue now on the Petri nets. So what exactly are Petri nets? So Petri nets are a kind of graph, and this is the mathematical definition, and I'll promise to you people this will also be the only mathematical definition I will show at this point. But as a summary, a Petri net has two different kinds of vertices, namely places and transitions. And it has a bunch of arcs which connect those places to its transitions. And of course, as most graphs, it has an initial state. And down below, you can see a picture of one of the most minimal Petri nets featuring an input and an output. So what features do we get from those Petri nets? So Petri nets are a fantastic way of describing distributed parallel systems. It's a bipartite graph, meaning there are two different kinds of vertices and they are not allowed to connect to the same kind. So places cannot connect to places, transitions cannot connect to transitions. And the whole thing is controlled using tokens. And a token, the presence of a token determines if a transition can be executed or not. All places connected to a transition need to have at least one token for the transition to be able to start an execution. Petri nets also allow to express task parallelism and data parallelism. As shown on the Petri net above, the data parallelism comes from the number of different tokens at the place P1, whereas the task parallelism comes from the splits in the Petri net. In this case, the transitions T2 and T3, which can in theory be executed simultaneously. So GPISpace uses three extensions to the natural Petri net definition. One of them being colored Petri nets. So a colored Petri net means a specific place can only have tokens having a certain type or a certain color. In the terms of computer science, that means a token in place P1, for example, has to be of type integer, whereas P2 will be of type string, for example. So another extension is timed transitions. A timed transition is a more realistic approach to Petri nets, where transitions and movement of tokens is not instantaneous. However, each movement of tokens has a certain runtime cost. And that's how you then get, like in the picture below, a certain transition might take longer than another one. So in this case, T3 is done before T2, and T4 now has to wait until both of them are done. And the final and probably most important extension is conditional transitions. So a conditional transition means that a transition is only allowed to be executed if a value of a token in one or all of the connected places fulfills a certain condition, like if counter equals 0. But why is this condition so important? Using these conditional transitions actually makes Petri nets Turing complete, which finally allows them to express any kind of program, which is a very important feature and allows the description of workflows, which are, for example, not possible with classical directed acyclic graphs. So in GPISpace, Petri nets are described using an XML-based workflow description, short an XPnet. In total, we have 3 elements. We have expression functions, module functions, and PetriNet functions. And one function tag is also the root tag of this format. So how do these look like? An expression function looks like the one below. It can, the head input and output are always the same. What the function actually does is, in this case, described using an expression. An expression is a custom language, usually used for very simple tasks like value plus 1, counter incrementation, passage, token pass-throughs. An important feature of expressions is expressions are executed on the agent and not on the worker, meaning expression functions are not scheduled on remote nodes. They are executed on the workflow engine itself. Now, module functions are written in C++ or C, and they are used for the heavy lifting, so they don't have any library restrictions whatsoever. And those are executed on the worker on their end. So they can have access to different hardware resources, to more compute, more memory, and are the most versatile functions available, or one of the most versatile functions available. Then the last one, a PetriNet function. So a PetriNet function uses as a definition of what it does, a PetriNet, a net. A PetriNet has places defined and transitions. And each transition on its own part refers to a function which gives it, which tells it what it can execute. Those functions are not limited to expression functions or module functions. It can, on its turn, also contain another PetriNet. So those 3 are basically the building blocks, the basis building blocks of PetriNets in GPISpace. So a lot of information, and I figured the best way of actually showing this is via an example, which we'll have in the next section. And a good example here, which is pretty minimal, but also shows a lot of complexity, is a reduction. In this step, we will be using a reduction, which does a simple summation. So in this, and on the right, you can see the PetriNet definition of the visual representation of the PetriNet on the left. So we have 2 places, our input place values and our output, and also intermediate value storage, sum. Sum is initialized using 0. Or if we wouldn't be using this summation, we would be using the neutral element of the operation. And so how does it work? I have a little example. We put in 4 values, 1, 2, 3, 4. Sum is initialized with 0. So as a first step, we'll take at random a value. There is no order, no predefined order at which values, tokens will be taken out of values into the transition. So in this case, we took number 2. Number 2 gets added to 0 and we get 2. So we repeat that process. Next we take 4, so now we have 6 in the sum. Repeat it. We take out a 1, so we have 7. And with the last one, so the final result in sum is 10. So now at this point, no more transitions can be fired, and the result can be retrieved through the output port of the PetriNet function. So how does that look like? GPISpace provides a Qt-based monitor tool, which has this whole process represented as a Gantt chart. For representation purposes, the reduce operation has been slowed down artificially with a timeout of, I believe, 2 seconds. So this is using one worker. As you can see, all of the steps you've seen before are now scheduled one after the other. And that's how that whole thing looks like. So one worker is of course boring, and that's not why we do HPC. So let's increase with 2 workers. How does it look like? Like, okay, first task, second task, and now, uh-oh, something went wrong. Like, yeah, we have 2 workers who are working, but overall we take exactly the same time as before. So what went wrong with our PetriNet? So PetriNets can be automatic added. They can have as many workers as you want. So each worker can take 1 token per transition and execute them all in parallel if possible. So in this case, our sum is the bottleneck. Our sum has only a single token, and each transition actually requires to have a token in each place in order to be fired. So the first token gets taken out from values and from sum. So sum is empty, which prevents the execution of the second token. But can we improve on this? The answer is yes, of course we can, using more PetriNets or using more places and more transitions. So in this case, to the previous definition, we renamed our sum place to L, or output. Value stays the same, and now we add 3 places. So we add a write, the R place, or write, and we have a transition which is only performing a pass through. On the right, you can see the transition for LHS. The transition for RHS looks actually exactly the same, just that left and right is flipped. And what do these 2 do? LHS and RHS are distributing the data. This is an operation that is extremely fast, and so they are distributing the data alternately using the tokens in the middle for control. But I know at this point this is hard to imagine. So we take again our previous example, 1, 2, 3, 4, and I added a few more intermediate steps because actually overall this is faster. So what does this look like? In the first step, you see LHS takes the first token, RHS takes the second token, and now L and R have each 1 token. Meaning in the next step, of course, reduce can be executed. But at the same time, the distribution of values can continue. So now the first result of reduce has been returned to values, and the remaining 2 values have been distributed to L and R. Now we execute again. So the previous value 5 will go to L, and the next result will go back to values and will be distributed on its side to reduce. To R. Now, one last step, we will calculate the last result. It goes back to values, and now LHS will take the last value and put it into L. At this point, we are done because there are no more transitions that can fire at this time. And so the final result is, as before, our 10. So using two workers, does this actually improve our situation? So the answer is yes, it does. And as you can note as well, we don't have 4 transitions actually, but only 3, which makes perfect sense as what a parallel reduction actually should be. So what can we conclude out of this for PetriNets? So PetriNets are a very powerful tool for describing workflow designs. They allow, with their parallel definition and mathematical definitions, they allow to actually design deadlock-free workflows. In addition to that, the normal software engineering part, you have automatic enforcement of modular code design. In addition, you have a separation of data and compute. The data is limited to what type of tokens can you have, and compute is separated into the transitions. You also get the benefit of automatic parallelization of workflows. However, as we've seen before, even if it can execute on as many workers as wanted, bottlenecks have to be taken care of, because those can reduce the overall performance. Another added benefit, here we are talking of high-level PetriNets. So independence of technologies for the transitions used is given. So we can, once we have a PetriNet, we can exchange the underlying implementation. In the examples shown so far, the C++ code was added directly into the PetriNet definition. However, a more usable scenario is actually to not add the C++ code itself, but just add the code to load a plugin. In that case, the plugin can be exchanged dynamically without having to recompile the PetriNet. So for most of our clients, this is true. They design a PetriNet once and then just exchange the underlying implementation for the overall pattern. It's even imaginable to, in theory, combine multiple different clusters or different node groups to run workflows using MPI or GPI2. Then in EPiGRAM-HS, this whole functionality got extended using heterogeneous module implementations, meaning you can have, for the same transition function, multiple different implementations for different devices. For example, FPGAs, GPU implementations using CUDA, CPU implementations. And not only that, you could even write one implementation using TDB, one implementation using OpenMP, using OMPSS, etc. And the other thing that was added, but is not added yet to the production code of GPISpace, is resource hierarchies. Resource hierarchies are similar to what Slurm is offering. It allows to fix certain resources to given tasks or certain given groups of tasks. So if you have a GPU task, of course you want that this task is executed on nodes that have a GPU. And so now you can say, okay, this task requires 2 GPUs, ideally on the same node. But again, this is not yet in production. It's a working prototype, and we're working on adding that functionality to the production GPISpace code. So I hope I could bring you, whoops, sorry, wrong error. I hope I could bring you PetriNets a little closer, also mainly because it's not that intuitive to work with PetriNets, especially when you just encounter them. And they are not as popular anymore as they used to be in today, especially not among application people. So I thank you for having me, for giving this webinar, and are there any questions?